Cisneria Engineering, Spain, and Hypothalamus Artificial Intelligence, USA. Presence optimizing rail public transport systems. Cisneria Engineering and Hypothalamus I have agreed on a technology alliance to jointly provide services to the special transport sectors, based on highly complex mathematical models. The technological capabilities of the two companies, in artificial intelligence and mathematical programming, make them ideal partners to face the multiple challenges that exist in advanced analytics applied to the transport sector. Due to the experience of the two companies, this alliance is particularly strong for the optimization of special transport systems such as the aviation industry, planning and operation of ports, and rail systems. The optimization-based applications for industries travel and transportation have been around for many years, due to the complexity of the business. The main services are workforce management, crew and drivers planning and scheduling, and staff rostering and scheduling. Fleet management, fleet planning and dispatching, network planning, and timetabling. Asset management, airport resource allocation, crane scheduling, vehicles maintenance, and warehouse resource scheduling. Yield management, pricing, and dynamic packaging. The benefits of operations research applications are cost takeout and operational efficiency, reduce costs of capital and cost-intensive resources and assets, capital expense avoidance or deferral, and better use of limited resources. Optimized workforce and improved customer service, increase quality of service and reactivity, more on-time deliveries and responsiveness, and improve employee effectiveness and satisfaction. Measurable ROI and improved profit, increased revenue and improved revenue mix. Improved market agility and reduced risk, respond to change quickly with improved planning. Smarter, greener planet, less carbon emissions and lower carbon footprint. Below applications of operations research in railway sector are presented. The following activities have been modeled using operations research in the rail freight industry. Routing, given the demand for rail freight transport, the set of operating policies under which routes will be assigned to trains and cargo must be established. Blocking, it specifies how blocks are constructed in each classification yard of the rail network. Blocks, they are the set of wagons that are grouped, since they share some initial portion of stations in their route, although their final destination is not the same. Classification yard, they are nodes that belong to the railway network where loading, unloading, classification of wagons, according to their destination, assembly of the same, etc. are carried out. Makeup policy, it specifies the list of possible blockages that can go on the output train. While the blocking models indicate the route to be followed by the load, and the distribution of the sorting work in the yards of the network, the routing and makeup models determine the routes and frequency of the trains, and the assignment of the blocks to the trains. In this way, the complete route and cargo allocation plan is composed of these three activities. Railway operations planning. Scheduling, timetabling. It is the generation of a schedule, which accommodates all train planning, satisfying the restrictions of the capacity of the railroad and the yard. Handling freight cars, it consists of the dynamic distribution of empty wagons in the network, so that the associated transport costs are minimized. Locomotive assignment, it is the assignment of the set of locomotives to the programmed trains, at the lowest cost, while satisfying the constraints of compactness and maintenance. The mathematical models used in railway operations planning are projected demand for rail transport services, optimization of the blocking process, construction of timetables for trains, allocation of locomotives to trains, and assignment of crews to trains. Due to the complexity of the process of design, the operation plan is decomposed into a series of steps. Feedback loops results in an iterative process between models. Metro systems. Metro de Madrid, Metro, optimization of staffing, train depots and lines. Metro needed better planning, knowledge and management of operations, to optimize resource scheduling, considering the large number of rules and limitations involved with labor policies, such as vested rights, shifts, breaks, union agreements, etc., and industry regulations. The planning must consider all the variables that have an impact on demand forecasting, such as weather conditions, vacations, breakdowns, seasonal variations, cultural and sporting events, etc. Using optimization software for scheduling, and real-time visualization for supervision, Metro has optimized in real-time two core business operations: staff assignment, and management of train depots and lines. Optimization software helps ensure that the 565 million riders Metro serves annually benefit from more responsive transit service and better managed operations. Metro has improved resource management, scheduling and adaptation of employee preferences, significantly increased efficiency in staff scheduling and train management, develop traffic plans faster and give passengers advanced traffic status, react faster to exceptional conditions, offering higher levels of customer satisfaction, and improve the quality and speed of decision-making. Netherlands Railways optimize the rolling stock allocation. Netherlands Railways, the nation's largest and Europe's busiest, 16.2 billion passenger kilometers by 2008, needed the ability to manage more trains and passengers within its 2008 infrastructure footprint. Netherlands Railways and IBM develop powerful algorithms to resource planning that can adapt scheduling and rolling stock allocations to short-term fluctuations in ridership. The mathematical tool was called ROSA, rolling stock allocation. With ROSA, Netherlands Railways can create an optimized operating plan that maximizes service quality, minimizes costs, and provides guidance for future infrastructure investments. The business benefits was $27.1 million in annual cost reduction through the optimization of rolling stock allocation, incremental revenue gain of $54.2 million through new approach to timetabling, 2% increase in on-time performance, shorter lead time for the development of new rolling stock allocation plans, and ability to accommodate additional ridership growth with minimal new infrastructure investments. Société Nationale des Chemins de Fer Français, SNCF, optimize rolling stock maintenance scheduling. SNCF developed a scheduling of locomotive maintenance operations model, based on a mix of traveled distance and time. The system functions are: long-term scheduling for budget analysis, 1 to 2 years, medium-term scheduling for workload, 1 to 8 months, and short-term scheduling, 1 to 4 weeks. The benefit: the mathematical model allowed SNCF to save 10% of maintenance costs. Japan Railways East uses optimization for Shinkansen timetabling. The Shinkansen, colloquially known in English as the bullet train, is a network of high-speed railway lines in Japan. Initially, it was built to connect distant Japanese regions with Tokyo, the capital. Beyond long-distance travel, some sections around the largest metropolitan areas are used as a commuter rail network. The main features of the system are: dynamic replanning of the Shinkansen lines in case of an unexpected failure. Recomputes a schedule that minimizes the total delays. Development of the optimization model took 1 year, and scheduling engine optimization solved the problem around 20 seconds, for 300 trains per day, on 4 crossing lines, servicing 37 train stations. The main benefit are: savings in total train delay time is up to 50%, and savings in recovery delay is up to 50%. Energy savings in train control optimization. The need for a clean environment is based on a rational consumption of energy. This covers all industries, and in general all human activities. Optimal train travel speed planning involves mathematical modeling to minimize energy consumption when the train has a predefined maximum arrival time. First, it must be considered that all industrial processes are variable speed, and that energy consumption, depending on the speed of the process, is nonlinear, it is exponential. This implies that, in the absence of economies of scale, the regulation of the speed of industrial processes is fundamental in the process of controlling energy consumption. Production facilities do not have a defined capacity, it is set according to the speed of the process, and the time that this speed lasts. That is a decision variable of industrial operations. The table presents the energy consumption versus speed of the AB 103 high-speed train. The column 2 shows the kWh consumed per kilometer for 3 speeds analyzed. The nonlinearity is noticeable. As a vehicle increases its speed, when it is operating above its maximum efficiency, the unit amount of fuel consumed increases, which implies higher variable costs. However, Increased speed means increased production capacity, which lowers investment costs due to increased vehicle use. The optimal decision is not obvious. The paper Optimal Trajectory Planning for Trains Using Mixed Integer Linear Programming presents a mathematical model that includes, in detail, the resistance of the route, such as slope, tunnels, and curves, and arbitrary speed restrictions. The objective function is a weighting between energy consumption and driving comfort, but it could be minimizing the cost of energy. The nonlinear function of energy consumption versus velocity is represented by a piecewise linear function. The optimal control problem is formulated as a mixed integer linear programming (MILP) problem, which can be efficiently solved by existing solvers. The case study considered two cases. For the first one, the total running time equal to 5.25 minutes, indicated by T1, black solid line, while for the second case is 10 minutes, indicated by T2, red dashed line. The speed of the train is presented in Figure 1. The optimal reference trajectories and the tensile and braking forces applied are shown in Figure 2. The energy consumption with running time T2 is lower than that with running time T1, but at the cost of a longer travel time. Figures 3 and 4. It is worth to note that the computation cost is very low for this MILP approach, is less than 10 minutes in 2011. Today the algorithm must be, at least, 1,000 times faster. The figure, extracted from another study, presents the relationship between the energy consumed and the travel time. The nonlinear behavior of the function is evident. The train journey can be modeled as an interleaved sequence of three states. Braking, when the train slowed down, eliminating energy consumption or recovering previously consumed energy, which can be used later, green line. Dwelling, when the train maintains a constant speed, minimizing energy consumption, and accelerating, when speed is increased, and energy is consumed according to the situation, red line. Railway alignment optimization. Railways are threatened by geological hazards whose disastrous effects include severe economic losses as well as serious casualties. It is vital to properly consider such dangerous geological impacts during a railway alignment optimization process. However, geological factors are complex, especially in mountainous regions. In addition, economic factors are also crucial in the design of the railway alignment. Therefore, optimizing railway alignment can be termed a bi-objective cost-risk decision-making process. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.